A person may come to Overpark expecting a nice jog around the beautiful green campus. However, the plans were interrupted as they see the patchy grass where some areas are way too long, possibly inhabiting snakes, whereas there are other areas that are way too short and yellowy and it ruins the aesthetics. Manual inspections of the entire area is time-consuming, which may be the cause of why some areas are overmowed, while others are overlooked. This is why we introduce Smart Landscape, green condition monitoring system that may solve all these problems.
Our solution is a web-based dashboard to monitor grass condition, featuring a live map, a detailed map with drone images, grass site monitoring, maintenance alerts, and history. This gives the user a bird's eye view of the condition of the grass in Oval Park. To start with, we will map out Oval Park into separate zones, as pictured here, and each zone is confined by the jogging track. Pictured here is the first iteration of our dashboard. So to make things easier to see, each zone will be highlighted in one of 4 colors: red, which represents immediate action; yellow, when the grass is too tall; blue, when the grass is too short, making it dry; and green, when it's in good condition. These zones are highlighted and for easy view. Clicking on the live map gives you an expanded view of the actual map, giving users an actual look of where the problem areas are. The detail view displays the most recent drone images, which the model has chosen to represent the zone's assigned classification. Clicking any one of the zones will pop up an info page, which allows you to see when the picture was taken and the status that it was assigned to. This also gives the option to override any wrong statuses classified by the model.
So for the prototyping plan, we plan 3 steps. So the first step is that we will do the data collection and labeling, which will capture the landscape photos across the UTP campus zones, specifically Oval Park, using smartphone or drone cameras. And we will label the datasets category using a spreadsheet or CSV or tools like Label-IMG. And next is the model training. We will train a model, which is CNN, in a Google Colab. And we will also utilize the transfer learning instead of training from the scratch to maximize the accuracy. And last thing is the dashboard and version control. We will build a dashboard using Streamlit or HTML to upload the photos and also output the status alert. And we will also manage the team collaboration, code tracking, and also the updates of the model via GitHub. So next is the testing and validation plan. So for the model level validation, we will do a 80/20 trend test dataset split to test the model. And we will also evaluate the precision, recall, and classification accuracy of the model via a confusion matrix. And we will also review the misclassified photos to identify the model weaknesses and make an improvement on the model. So next is the dashboard functionality. We will verify the rule figures is correct and also test the cases such as blurry uploads to ensure 0 dashboard crashes. And lastly is the usability. We will measure the benchmark processing speed from image upload to final dashboard instruction to make sure the model is processing fast.
For the impact of our system, we evaluate it across ESG criteria and its value to our stakeholder. Environmentally and socially, it helps prevent flood and water waste while maintaining a pleasant campus landscape for the UTP community. From a government perspective, it transitioned UTP to a data-driven strategy. But the ultimate value proposition is clear. For PPMD and our cleaner, the direct errant significantly reduce grass work and physical strain. And for UTP management, it optimizes the budget and supports our smart campus initiative without replacing human oversight.
Moving on to challenges, we must account on a few operational constraints. The first one is weather. So strong wind, rain, or maybe cloud cover will cause flight instability and lower quality image. And operationally, drones are limited to 20 to 40 minutes flight per battery. So meaning larger area will require more run and equipment maintenance in the long run. Additionally, implementation require technical expertise from certified drone pilot to engineers who will train our machine learning model. And finally, we must comply with the Civil Aviation Authority regulation, including strict safety guidelines such as permit and the 120-meter altitude, reducing the need for manual field survey and enable faster inspection and early detection of dry patches and overgrown grass, allowing proactive groundskeeping and smarter resource management.